So we have covered multi-arm bandits in the last two classes, and there the task was always try to choose the best action. Obviously, we had greedy, epsilon greedy, and many other methods because the best action was not known to us. But the scenario was that if it was stationary, then there is always exactly one. I mean, there is exactly one best action. Okay, and the goal is essentially to get there, estimate what is that best action. In case of non-stationary also, the goal was track the best action as it changes over time only. So it changed over time only and nothing else, right? So this was a kind of a simplified scenario. And what we would like to do is we would like to get to a more realistic scenario where the context also matters. So for example, not only the time changes, but also the situation changes. Okay. Um, okay, so we'll see the examples of that in a while. So towards more realistic setting, what we want is there can be more than one situation. So just imagine for anything that you want to do, uh, the same action may not be the most beneficial, even looking at long-term thing and so on, most beneficial um, in all the places, right? So depending on the situation, you want to also change the action and the time. So not only the time, but also the situation or the context. So then our goal would be to learn a mapping from situation and time to what should be the action for now. Okay. So our goal is to learn that kind of a mapping, and we'll formalize that with Markov decision process. Okay, MDP. I think you must have seen Markov process in other courses, or we have actually just touched upon it when we did PageRank. But in the context of reinforcement learning, we need to understand it, and the use of MDP in this is quite different. So we need to actually go through this in more detail. Okay, so one picture that you will see everywhere whenever you think, whenever you try to learn reinforcement learning is this agent environment interface, where uh, the the agent is the learner and the decision maker, the person or the robot or whatever, or the machine, right? So who is taking the actions, okay, or deciding which action to take. So what the agent does is agent interacts with the environment. Now, what is the environment? Now, the boundary between the agent and environment can sometimes be blurry, but essentially anything that the agent interacts with and everything outside the scope of the agent. Physically, if you think about a human scenario, it is possible that the environment is within your body, right? So it's also possible that the environment, the body, your body is part of the environment, but the decision making part is the agent. Okay, so so environment is essentially everything that is outside the decision, outside the scope of the agent. Now, at this point, it's pretty high level. You can all try to think about examples. I'm not going into too many of them, but we will come across examples and things like that in the course of the classes that we'll have. So what happens is the agent takes an action, let's say at time step t, takes an action at, and the environment gives a reward. Okay, so reward rt plus 1, and changes the environment to a new state st plus 1. Okay, now, so this is obviously a result of action t. What would have happened before that? So this goes on, right? So what would have happened before that is uh, the reward rt and state st of the environment influence the agent to take action t. So essentially it kind of goes on in this way. So that's essentially the agent environment interface. So for t is equal to 0, you typically, let's say, assume have no reward. So this is not applicable, but the state 0, right? So you have some state 0, the agent takes a0 maybe, or depends on how you start it, and then it goes to s1 and so on. Okay, so that is basically what happens. Um, Okay, so keeping this diagram in mind, let's try to now define a finite Markov decision process where uh, S, all the states, okay, belong to a set of states. S is the set of states, R is the set of rewards, and A is the set of actions. All possible states, rewards, and actions. And let's, as of now, think that all these are all finite sets. If these are all finite sets, then what happens is the sequence, we get a sequence or trajectory of actions, rewards, and states like this. So state 0, action 0, I get reward 1, state 1, action 1. Then depending, reward 1, state 1. Depending on that, I take action 1, I get reward 2, state 2, and so on. Now, obviously, what we are saying here is that the agent decides, and our goal is how do we decide, right? So our goal is essentially making the agent learn better to make better decisions, right? So so that means that decision process is what we want to improve. So for finite MDP, okay, we have a probability distribution that is something like this, that probability given state S, action T, what is the probability of getting reward R and going to state S prime? Now, this dot is in the book, Barton's book. They give a dot when they define something. I think in my slides I have done it sometimes and sometimes not, but yeah, maybe I'll go over that once again and try to be consistent. Maybe it's not required. We understand that we are defining it. So this means probability that ST is equal to S prime or T is equal to R, given the previous state was S and the previous action was A. Okay, and this is a definition over all possible states S and S prime, all possible actions A, and all possible rewards R. All right, now let's think about this a bit more carefully. What are the differences from what we have seen before, that is the multi-arm bandit case, right? So what happened there was no state. First of all, there was no state. What there was, obviously, yeah, sometimes the probability of taking actions differed. So we could or we could not take some action sometimes, so that is fine. So given an action, we got a reward, and there was a probability of getting this reward given this action and all, right? But the state thing was not there at all. Now what this tells you is that even if you are in a state S and you take action A, it is not totally certain where you will land up. Not only that the reward may differ, but also your state may also differ. I mean, just imagine anything that happens, right, in the real world. I mean, seemingly in the same state, you do the same thing. It doesn't mean that you will get exactly the same result, right? I mean, so that is the scenario. So that's where the probability function P coming up here. Now, also what we obviously have then, since P is a probability, we have this, that the sum over all possible states S prime and all possible rewards R, P of S prime R given previous state S and action A must be 1. Okay, so that's because P is actually a probability distribution. Now, this is the most important property, Markov property. The probabilities of each possible values of ST and RT, right, depends only on the previous state and the action, and not any state or action before that, right? So when we talked about PageRank, we said we were talking about a random surfer, and what we said was where the surfer will go from a particular node depends only on this node, does not depend on where it came from before this, right? So essentially, same thing, it's more generalized here, that for any particular given, yeah, I mean, whether if you are at state st minus 1 and you are taking action at minus 1, these two only will determine the probabilities of the future state and the future reward that immediately happens after this. Now, this might seem like it's a limitation on the whole process or assumption. Yeah, in certain sense it is. But the assumption essentially is that the state must be able to include all information, all necessary information that matters for the future. So wherever I am today is a result of everything that I have done and I have learned, and that's all matters, right? So that's all matters, and that agent me must encode everything about that perfectly. So so that's basically what the assumption is. So in a way, this assumption is slightly restrictive, but again, uh, in a perfectly modeled state, you can feel that, well, that's how the world goes, right? So the world actually goes that way, that what is happening, what will happen depends exactly on everything just before that, and no, and then and so on. So then you can actually erase the dependency on things before that. Okay, so that's essentially this Markov property. Okay, any question as of now? Is this probability distribution clear and agent interface, agent environment interface clear? Okay, all right. So then let's actually look at an example. This is from the book, a simplified recycling robot. So we have seen the PageRank example, wave graph, and so on, but that was a very simplified one. We want to see a little bit complicated MDP. So yeah, let's say a mobile robot. Okay, uh, there are uh, there are lots of mobile vacuum cleaners going around on Amazon nowadays. I know people who are contemplating buying one. Lockdown and all those things. So it's similar. Mm, so what is this mobile robot trying to do? It needs to collect empty soda cans in office and put them into the bin. So suppose I know people empty soda can or any empty paper cups, coffee cups, or whatever. So in an office, people drink soda and then just keep the can on the desk maybe and things like that, or bring it to a table. Uh, Essentially, the job of the robot is to collect them and put them into the right recycling bin. And suppose it has all the necessary sensors and arms, so that's not important in our discussion. So it can detect, yes, it's a can that I need to put, and it can actually hold it and put it. Okay, so those are, yeah, they are AI, right? So you have to detect, so that's actually a computer vision or image detection kind of a technique thing. So it's not what we are interested in right now. What we are interested in right now is the following thing. It runs on a rechargeable battery. Okay, so it runs on a rechargeable battery, and ideally what we want is it should decide itself when to recharge itself. So it should be totally automated and we should not actually have to bother about it at all. So that is what we are actually mainly focused on at this point of time. So again, since it's simplified, let's say there are two states indicating the battery level. You can already see that if you want to completely model this realistically, then the number of states, number of battery levels will be infinite and so on. So we'll not actually have a finite MDP, but I mean, you can pretty much approximate it using a finite MDP. So high or low, let's say two states, you instead of high or low, you can have 1 to 10, 0 to 100, or whatever you want. But let's say high or low, to two states indicating battery level. So whether it has high battery, the charge is high or charge is low. three actions. One is, okay, go around the office, and so it can go around the office and search for an empty can. Okay, so it will go around the office, look at the tables whether there is an empty can. Okay, so that's one action, search. Second is wait. Okay, just wait there, don't go around. uh, Maybe wait and somebody will come and bring a can near you, maybe keep it on the table or something like that. And the third is go to your home base and get recharged. So in the office there is one corner where there is a plug point, and it can actually connect itself to it, and it get recharged. Okay, so now uh, what should be the state action mapping? So what should it do at what point of time? When it has obviously high battery, so when it has high battery, there is no point recharging it. So the action when your state is high should be either search or wait. And let's say when the battery is low, it can either do a search or wait or a recharge. Okay, so these are the, let's say, I mean, you can also do search, wait, and recharge, and basically it's not with equal probability, right? We'll actually assign probabilities. So given low battery, what it should do, the action, we should assign probabilities. So essentially what it means is that a high, the probability of recharge given the battery level high is, we are already saying it, setting it to 0, so we are not considering that. Okay, so now let's say how the rewards will be assigned. So our goal is that this robot should keep the office, clean from lying around cans. Okay, so that means a positive reward should be given for finding a can and dumping it into the bin. So whenever it does that, it gets a can and dumps it into the bin, it gets some positive number, so some positive reward. Call it +1 or some any plus constant something. But what we don't want is it goes around, tries to find cans, and the battery totally goes down. Okay, and then it kind of shuts down, not at the home base. So shuts down without coming back to the home base for recharging, and then somebody has to go and rescue the robot manually and bring it back to the home base. So this is something we don't want. So if this happens, then there is a high negative reward. That means a high penalty. So usually you find cans, you keep getting small positive rewards and so on, and you keep doing that. That is what is ideal. Do not try to avoid this penalty. So that's what it should be. That's what should be the goal of this robot. By the way, the words goal and reward and all these things will be formalized very soon. But anyway, so that means whenever the robot goes on searching, the chance of reward, okay, or the expected reward or search is higher than our wait or our recharge, right? So when it is recharging, it cannot find a can. When it's waiting, there is a much lower probability of finding a can, right? When it is searching, the probability of finding a can, and hence probability of getting a expected value of the reward, is higher than other actions. But when it goes around searching, it will drain battery much faster, right? So that's essentially the main trade-off. So something like this will happen. Now this table is from the book, but let's actually investigate this to understand what we mean. So this is probability of going to a new state given old state and some action. So this is the old state, this is the action, this is the new state. So if the battery was already high, I keep searching with probability alpha, and this is again a simplified model I told you, right? So this can be actually calculated based on exact battery percentage and so on. So probability alpha, the battery remains high, but with probability 1 minus alpha, then the battery can become low. Okay, so high, search, the battery can become low. In either case, as long as you are searching, the chance of, the reward R, which is again a function of the state action and the future state, right, is this. if the battery is already low, you keep searching, right? Uh, the so basically this means that battery is low, you keep searching, and your battery totally went down. So the robot became the robot shut itself down, and somebody came and rescued. So then and put it on recharge. So then the battery becomes high. So don't get misled by this thing. Low search, high means in the meantime it had to be rescued. So let's say the reward is -3. Okay, high negative reward. And low search low is, well, I mean, it doesn't lose the full battery. The battery remains low. Suppose that probability is beta and the other probability is 1 by beta and so on. So high weight, uh, high, if you simply wait, it will remain high, but then the reward also should be R weight. It should be less than R search, right? So reward also should be less than R search. High weight probability becoming low is, let's say, almost zero. So it's like standby mode, so you can stay for a long time, and so on. So, okay, so basically this is your probability distribution that we are looking at. And we can also draw the transition graph. So these are the states, high and low, and these small nodes, so these are the state nodes, and the small nodes are the action nodes. Okay, so from this state high, if you wait with probability 1, you get reward R weight, you stay at high. Okay, so essentially, uh, um, yeah, essentially it's state, action, probability, and reward, and you come back to another state or go to another state. So let's say from high, you search with probability alpha. You expected rewarded are search, but you remain at high. With probability 1 minus alpha, you go to low. Okay, so I leave you at this. uh, this is what a transition graph of an MDP is. I believe this should be easy to comprehend. All right, so now what we have seen is, we have seen that we can actually model a much more realistic scenario using MDP. Okay, and MDP is actually, for classical reinforcement learning, it's the base of lot of methods, some of which we will probably be able to cover before our course ends. So then let's formalize goals and rewards. So what is a goal? Uh, the reward is something we have been already talking about, and we have informally understood that the goal is getting high reward, right? So it's like making more money kind of a thing. So rewards are essentially signals whether the agent is making progress towards the goal or not. But goal is something which we have not formally defined. Now, what should the reward be, and what is actually our goal? Now, we said when we talked about greedy and not so greedy methods, that the notion of the the whole idea is not to maximize the reward immediately, um, or not, rather not always to maximize the reward immediately, but in the long run you should get more rewards. Total reward should be more. So the notion of maximizing long term reward should coincide with achieving the goal, right? So let's say example one, make a robot learn to escape from a maze. Okay, so if that is your goal, then there is actually no sub goal. So then the reward should be, let's say, -1 for every passing time step. Let's say every minute goes by and you don't escape, you get a -1. But the reward is something positive when you have actually finished what you wanted to, right? So you could escape the maze. Or let's say, make a machine learn to play chess. So in chess, what is the goal? In chess, you can think of the goal is obviously winning, right? So winning the game is the goal. But are there sub goals? So obviously, one straightforward way of formulating the reward is if you put +1 for winning, -1 for losing, 0 for a draw. Now, I believe most of you have played chess. In chess, what we can do, we can actually take the opponent's pieces, right? So if we take the opponent's pieces, the opponent's strength goes down, and obviously indirectly we strengthen our position in the game, and we will probably have more chance of winning. Now, there is a bit of a problem if we formulate only that as a part of the reward. So what if we say +1 for taking a piece of the opponent and -1 for losing a piece if the opponent takes one piece of me. Okay. Now anybody has a guess what would be the problem if this is all that is there in the rewards? See, the point is we may have a goal, but the reward is what the agent is actually looking at, right? So the agent is trying to maximize the reward. So what will happen in this case? Anybody? Okay, I mean, one thing that can happen, I'm not saying that will happen all the time, is maybe maybe you are in a very bad situation in the game, and you should rather do something with your defense rather than trying to attack somewhere else and take a piece, right? So but the agent doesn't know that. The agent wants to maximize the reward, and the agent will, even at the cost of losing the game, the agent may actually take another piece of the opponent, right? So this can happen if winning and losing is not extremely emphasized in the reward system, because that's your goal. So the whole message here is that yeah, or what can happen is that it will actually aim to take all the pieces of the opponents and actually never go for the formal checkmate thing. So what can the main message here is the goal that you want to achieve through the agent, you need to formulate that into the reward system properly. It is okay to set rewards for sub goals, but you have to be a bit careful. I mean, it should not be just sub goals. Piecewise sub goals are may not add up to your main goal. Okay, so this basically is the it's actually a conceptual thing that we want to do for goals and rewards. Now, now let's see how we formalize rewards in case of two different kinds of tasks. So one of them is episodic task. Informally, again, the goal is to maximize the cumulative reward in the long run. So episodic task is one where there is a natural notion of a final or terminal state. For example, a game, right? One match finishes, one game finishes. We can think of that as one episode because the next game starts and everything, all states gets reset, right? When the next game starts, all states gets reset. The agent keeps learning. Even if the agent won or lost doesn't matter, maybe, but the agent keeps learning. So the time step goes forward. Okay. So the time step t goes forward, but at some t, this episode ended and the next episode starts with everything being reset. Okay. So that's basically these kind of tasks are episodic task. A robot wants to escape the maze, right? So yeah, somebody has a question. Okay, a robot wants to escape the maze. Once escaped, maybe took a very long time, right? But then that episode ended. You want to solve the Rubik's cube, okay? So yeah, maybe first time you took a very long time, but that episode ended, and then you are given another scrambled one. So something like that. Now the learning does not finish, but once a game is finished, the next game will start freshly, so the states are reset. So if the current time step is t, what we want to do is we want to maximize the expected return, okay, and where gt is the expected return, that is from now on the rewards until or till the episode ends. So that is rt plus 1. Oh, sorry, this should be rt plus 2. I'll correct it later. Plus dot 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 rt, where t is the time of termination, and it's actually a random variable because sometimes the next step can be, sometimes that capital T can actually be t itself and some t plus 1 itself, and sometimes it can be much larger. So that will actually vary from episode to episode. Okay. All right. So these are episodic tasks, but there are situations where a task is not episodic. It's like continuing. Okay. So for continuing tasks, what happens is there is no identifiable episode. Okay, rather goes on. It kind of goes on. Things don't get reset. Okay, so ongoing process control task. Okay, or maybe you are actually training a recommender system, news recommender system for using reinforcement learning, some personalization task, how the user reacts. That's your environment then, so on. So there is nothing really, I mean, often there is no reset of that sort. There is no terminal state, or you can think of it as the termination number t, the time step for which it terminates is kind of infinity. So then what would happen? Then the rewards also can be infinity, right? Because if you always get a reward like a plus one, plus one, plus one, or if you get plus one infinitely many times, your reward will be infinity. Then what are you actually trying to maximize? I mean, everything is infinity. So that's when people use the notion of discounting, um, like exponentially reducing weights. But we have seen this kind of a thing before for past things. Now this is for future. So reduce weights of rewards in the future exponentially. So what we do is instead of gt equal to rt plus 1 plus rt plus 2 plus rt plus 3 dot 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 dot, we'll do RT plus 1 plus gamma times RT plus 2 plus gamma square times RT plus 3, etc. Okay, so formally the sum is an infinite sum gamma to the power k times RT plus k plus 1, where gamma is a number from number within 0 and 1, this interval, and it's called the discount rate. So it's a parameter. Now let's see what happens for different gamma, right? So what if the gamma is 0? So what if the gamma is 0? So this discount rate, it kind of shows you or determines how much the agent is focused into the future, how much long term is it thinking. Okay, so for gamma is equal to 0, all the terms in the future are 0, so only rt plus 1 is remaining. So this is only focusing on the next reward. So this in real life, it's similar to instant gratification, right? So I immediately want to get whatever reward I can get. I don't uh, really bother about what's going to happen to me in future, right? uh, Now more the gamma, obviously gamma cannot be more than 1, but and gamma should actually not be 1 either, because then we are not discounting anything. So it should be something less than 1, but if it is large, then the more futuristic the agent is, right? So for any gamma less than 1, this sum, however, this sum converges to a finite number, right? Because the infinite sum, uh, because this number, this infinite sum is just simply sum of the GP series, that's 1 by 1 minus gamma. And if all the rewards, suppose there is a maximum of that. So suppose there is a bound, it's all the rewards are bounded by some number r, then this whole sum will actually be this quantity times that bound, right? So essentially then we are saved from this infinite reward scenario. I mean, where different scenarios all are infinite rewards, we cannot really think about maximizing that. So what we now can do is we can think about maximizing the discounted reward or discounted return, that we call. So return is essentially the expected future reward. Okay, expected future reward is what we call return. Okay, any question at this point? All right. So so then we can actually see another interesting relationship between the expected returns of successive time steps. So what is the return? This is the expected return, that is the cumulative rewards into the future, right? So gt is the expected return at time t, and gt plus 1 will be the expected return at time next time step, and so on. So let's say gt, so gt is this, right? rt plus 1 plus gamma rt plus 2 gamma square rt plus 3 dot dot dot. what we can do, we can just take gamma common here. Okay, take gamma out from the second term onwards. So then RT plus 1 plus gamma times RT plus 2 plus gamma RT plus 3 and so on. So all the powers just reduced by 1 here, right? So then this thing is essentially GT plus 1, right? So this is the GT, this is the GT plus 1. So what we get is RT plus 1 time plus gamma GT plus 1. So very important formula, GT, the expected return at time step t, is the immediate reward that you're going to get plus the discounted uh, reward of the next step. Okay, so that's the relationship between expected returns of successive time steps. Yeah, so now we'll formalize. Actually, in this whole class, we'll essentially formalize the notations and notions. And next class onwards, we'll actually see some methods. Okay, so and what we'll see policies, right? So what are policies? We have loosely used the word policy when we did greedy and stuff like that before, and we can kind of understand what it means. It means that what would be our approach towards selecting the next action. But formally, there is nothing called approach. There are only probabilities, right? So whatever we are thinking, we will actually choose according to some probabilities. So essentially what happens is reinforcement learning algorithms, we should have the learning here, involves estimating some value function, right? So some value function means expected reward and stuff like that, um, or something like that. But what we'll actually define the value function formally here. And the value function should be a measure of how good it is for the agent to be in a particular state in terms of expected return. So good means, should I be here? Should I be in this state? Well, if being in this state is beneficial for me in the long run, or whatever way we have discounted the future, okay, so then yes, right? So that's basically it. Now the value functions depends on states or state action pair. So it can be only on state, or it can be dependent on state and action. And a policy is a mapping from states to probabilities of selecting an action. So this is the formal way of saying our approach of what we should do next. So it's a mapping from, given that I am in this state, the probabilities of selecting different actions. So let's say given, and right now I am taking a class, I must be finishing whatever is in the slide, right? So that has very high probability. So basically, so that's for anything in the world that happens. For many things, we can actually say, okay, given the scenario now, the next thing is going to happen is most likely that. So that's the policy. But that's in the real world. For the agent also needs to have proper knowledge. Otherwise, everything is random, right? So like the epsilon greedy thing, the non-greedy action selection is a total random one. So that's typically not so good all the time, right? So mapping from a state to probabilities of selecting an action. Now, suppose an agent is following policy pi at time t, then pi of a given s is probability that it will select action A given that it is right now in state S. Now, you might be thinking there is a P that we talked about before. P given a state and an action, what is the probability of getting a reward R and going to state S prime, right? We also looked at that MDP example of that recycling robot thing. So that was our state, right? Now, so that was our P, sorry. Now, what we see here is a different one. This is a pi. The P was given a state and an action. It would have given us probability of a reward and going to a new state. This is given a state, the probabilities of choosing the actions. Okay, so we'll actually there is a diagram called backup diagram. We'll see that in a while. That will clearly tell you the difference. So that the value function v pi s of a state S under policy pi is expected return when the agent starts at state S and keeps following a certain policy pi. Okay, so in other words, now this yeah, these formulas may look a bit daunting, but that's not. So B pi S is the expected return if I start at S and I keep following my policy pi. So that means expected return, okay, of expected GT, right? GT is my expected, GT is my return if I start at S. If I start at S and keep following policy pi. That means GT can be written as the sum of gamma to the power k or t plus k plus 1. So this sum given st is equal to s for all s, right? So that's what the definition v pi s is. So for any s in my set of states, v pi s is defined this way. Now the action value function, so this is the value function. The action value function is value of taking an action A in state S under policy pi. So it's nothing but it's basically q pi s. This is expected value of GT. Now this was only for the value function was expected value of GT given that I am at S, at state S. This is the expected value of GT given that I am at state S and taking action A. Okay, so it's just the condition is modified here. All right, so we'll finish this class with the Bellman equation today. So yeah, what we have just seen is the value function, right? So just this formula. So from that definition, what we get is the value function is the expected value of GT given ST is S. And since we have just seen before, GT is RT plus 1 plus gamma GT plus 1, right? The next reward plus gamma times the next GT, right? So since this, we can actually replace it. Okay. And now, okay, so let's, so this from here to here, what we are doing essentially is we want to compute the expected value of R, this reward plus gamma GT plus 1. We are bringing it here. We are bringing it here over all possible rewards R, over all possible next states S prime, and all possible actions I can take, multiplied or weighted by the probability of taking that action. So the probability now, given that I'm at S, probability of taking action A is pi A S, pi A given S. My probabilities P gives me, now I am at S, taking action A, S probability of S prime and R. And since I'm summing over that R is next R is this plus gamma times. Now I simply have the expected E pi of GT plus 1, this, right? So it's basically expanding this expectation formula. And now here we are actually taking a sum over all possible states, all possible rewards, and all possible actions. So I'm just simplifying it instead of writing it in full and simplifying these two sums. I'm actually making it one because this is taken over all possible combinations of S prime and R. P S prime R given SA, and this thing is essentially B pi S, right? B pi S is this. So this is B pi S prime. Right? This is essentially B pi S prime. So R plus gamma times V pi S prime. So what this does, so this is called the Bellman equation. And what this gives us is it's a relationship between the value of a state S and the values of its successor states S prime. What is the relationship? Average over all possible actions, weighting them according to the probability, okay, and all possible subsequent states and rewards, okay, weighting them and then multiplying by the discounting factor or discounting rate, you have the values of the all possible subsequent states. All right. So there is this new there is this diagram that we can draw now. So suppose you are at state S, you you with probability. So given policy pi is the gives you the probabilities of choosing different actions. So you can choose any of the actions. Now in this diagram we have only drawn three. Suppose this is your action A, and suppose you have taken action A. So based on the state and the action, the probability distribution P will give you which state you will go next, and also the reward, right? So the reward will also be obtained somewhere here. So essentially, the pi is applicable for this step, which action I will take, and the P is applicable for once you have taken the action, what will be the outcome, or rather what will be the outcome reward, and what will be the next state that I will go into. Okay, so this is called the backup diagram for V pi. All right, so that's kind of what we have done for today. Next class, I think there's a little bit remaining in MDP, optimal policies and near optimal policies. So we'll look at that, and then we'll actually get into. I'll try to give you an overview. So instead of going into each of the different topics of, policies, I will actually try to cover more width. So yeah, so we'll cover Monte Carlo, we'll cover a little bit of dynamic programming, which you probably already know from algorithms. So you already know the concept of dynamic programming. Monte Carlo, I'm not so sure. So we'll actually cover them. We'll try to cover them in next 2 classes or so, and then we'll go into function approximation, where we use the usual, machine learning techniques kind of things. Okay, so gradient, stochastic gradient, um, ascent, and all those things that we have seen in the previous class. All right, so any immediate question?
Sir?
Mm-hmm.
So here pi and p, these two distributions we don't know, right? Like we will try to estimate them as we go
Uh,
on.
the P we don't know. Pi is what we are setting. Pi is the policy.
So we will set them from before only, like depending on which state,
We'll obviously
which
start.
action we will take.
We'll start with something definitely. So pi is our policy. So our means if we are the agent, right? We are trying to train the agent. So pi is that policy. So pi must be our control, but P is not in our
Okay.
control. Right?
Okay.
See, what action I will take is my control, but what will happen to things outside my scope is not in my control.
Okay. So this p we will try to like estimate as we
Right.
go on.
So rather we will actually try to estimate the values. So yeah, so we'll try to modify pi so that we get high V.
Okay.
Right? Yeah. Okay, so that's it then. Then I'll upload the materials by this evening, and then see you on Thursday.